taste of physics. Today, we will explore an innovative way to measure how complex systems evolve towards equilibrium. I will go over my 2023 paper in collaboration with Ari Kapulkin and Arjendo Pataniak from Carleton College. We introduce a novel metric, Pi-entropy, that tracks how ensembles of initial states mix and lose structure over time, all with striking computational efficiency. We first test this approach with the logistic map, a one-dimensional chaotic system that is confined to move between 0 and 1. For R values between around 3.6 and 4, the system is chaotic with some windows of periodicity. For a chaotic situation, depending on the initial value x1, the system will follow a specific path. Its neighbors will follow a similar path at the beginning, but soon will diverge as iterations increase. That's the signature of chaos. We want to study how an ordered ensemble of elements braid and entangled their paths. In this figure, we see an ensemble made of 1000 initial points narrowly confined between x equals to 0.45 and 0.55. They begin to spread and entangle across iterations. The density morphs from tightly clustered to fully dispersed. You can look at panel G. This motion illustrates how deterministic chaos disperses information. Neighbors lose their neighbors as time evolves. Panels H and I offer two complementary perspectives. In H, individual trajectories are colored from dark blue, starting near 0.45, to light blue, near 0.55, revealing how initially ordered neighbors intertwine chaotically. Panel I presents the evolution of the ensemble as a temporal landscape, the horizontal axis as ensemble index, and the vertical axis as time, with the color mapping the state or position in phase space. Early regularity fades into an entangled mosaic. This is a clear statement of the structure eroding over time. Finally, panel J presents the new metric that we introduce, Pi-entropy. This is the permutation entropy computed using the positions of each neighboring element of the ensemble at the same iteration. Initially, ordered ensembles begin with pi equals to 0. As the states mix, pi climbs on an S-shaped curve, ultimately saturating at pi equals to 1. The fully shuffled maximum entropy limit. This behavior mirrors thermodynamic entropy growth, but crucially, pi is far easier to compute using ordinal patterns rather than full density functions. Figure 2 tests robustness. In 2a, different ensembles with varying initial densities and widths evolve at first differently, but each pi-entropy curve traces the characteristic S-shape. What's more revealing is 2b. We introduce the EPS, the entropy phase space, by plotting pi dot versus pi. This shows all ensembles converging to a common trajectory from 0, 0 to 1, 0. This universality highlights a shared relaxation path regardless of starting conditions. Figure 3 expands our view. Panel A shows logistic maps with different chaos levels by using different values of the control parameter R. Higher values of R indicate higher chaos. Higher chaos speeds up entropy growth, seen in a steeper S-curve. This connects pi's growth rate to the Lyapunov exponent lambda. Panel B extends this to other one-dimensional maps, the cubic, the sine, the recurse, and the cusp maps, all demonstrating similar transitions. Across maps, more chaotic systems lead to faster mixing. reinforcing pi as a universal proxy for entropy. We define the exponent alpha as the slope of the linear regime in entropy phase space. Digging deeper, panel D concretely links the relaxation exponent alpha extracted from the linear regime of EPS, the entropy phase space, to the Lyapunov exponent lambda. As lambda climbs, so does alpha. In essence, more chaotic systems shuffle information faster, and pi's growth rate quantifies this exquisitely. Turning to two dimensions, the Chirikov standard map unfolds new complexity. This is a chaotic map with one control parameter k and two dimensions p and theta. In panels 4a through 4c, for high values of the kick strength k, the map's phase space is largely chaotic. Here pi evolves swiftly, mirroring behavior seen in the uniformly hyperbolic cat map that I don't show in this video. The EPS, the entropy phase space, maintains a steady monotonic drift similar to the one found in one-dimensional chaos, signaling rapid homogenization. This contrasts with low k, as you can see in panel 4b, that shows pi exhibiting periodic oscillations, a signature of mixed phase space dynamics, where islands of stability coexist with chaotic seas. In panel 4f, EPS traces a spiraling descent toward equilibrium. The relaxation envelope follows the same trend as in fully chaotic regimes, but oscillations overlap this envelope, introducing nuance signatures tied to the initial conditions of the ensemble, the localization and the size. Figure 5 takes a closer look. When initial ensembles of different sizes and centered at the same point are compared, the pi oscillatory traces differ, but their envelopes match in slope. No matter how localized the start, the average rate of entropy growth remains consistent. This underlines the robustness of relaxation dynamics captured by pi. The bottom row of these figures shows on the left the initial location of the different ensembles, all centered at the origin, 0, 0. The figure in the middle shows the portion of phase space that they explore, and the figure on the right is the phase space of the standard map for k equals to 1.0. In summary, Pi-entropy offers a powerful, efficient window into how complex ensembles thermalize. It captures universal relaxation patterns through S-shaped growth, ties to chaos strength via Lyapunov exponents, and reveals rich dynamical layering in mixed phase spaces with oscillations and envelopes. Best of all, it does so by tracking only a few hundred or thousand trajectories, making it highly promising for experimental validation. The next step now is to apply this Pi-entropy to real-world data to explore how entropy builds up in an interacting ensemble. Currently, some of the authors are working with data from biological systems with promising results. Well, thank you for joining me in this visual journey into ensemble entropy dynamics. If you'd like to dive deeper into how to compute pi, apply it in experiments, or explore its connections to real-world systems, here I leave the link to the paper published in 2023 in the Journal of Physics Complexity. Thanks for watching, and may science be with you.